Mm, I am going to discuss about scene construction from multiple views. Scene construction from multiple views means reconstructing a 3D scene using multiple 2D images. It is a fundamental problem in computer vision because it helps machines to understand the 3D world. This concept is widely used in robotics, augmented reality, virtual reality, and autonomous systems. The real world exists in three dimensions, but images captured by cameras are only two-dimensional projections. So, depth information is lost during imaging. The goal of scene reconstructing is to recover the geometry, structure, and depth of scene. To achieve this, we use multi-view geometry and optimization technique. So the input consists of multiple images taken from different viewpoints. From these images, we estimate the 3D coordinate of points in the scene and the camera parameters. The final output is a 3D model, which can be either sparse or dense depending on method used. In a single image has limitations such as depth ambiguity and scale ambiguity. This means we cannot accurately determine distance or size of a image. Multiple views provide depth information using disparity, which improves accuracy. This is based on the parallax effect, where objects appear to shift between views. So a single 3D point appears at a different position in different images. Geometry defines the relationship between these projections. The key idea is to find correspondence between images and understand how projection work. This allows us to estimate depth. Next is camera model. The pinhole camera model is used to describe how images are formed. It explains how a 3D point is projected onto a 2D image. Intrinsic parameters describe the internal properties of the camera, while extrinsic parameters describe its position and orientation. The projection matrix combine intrinsic and extrinsic parameters. The equation x equals p multiplied by x represent the mapping from 3D point to a 2D point. Homogeneous coordinates are used for mathematical convenience. This equation convert world coordinate into image coordinate. Next is correspondence problem. The correspondence problem involves identifying the same physical point in different images. This is the most critical step in reconstruction. Challenges include occlusion, lighting changes, and repetitive pattern which make matching difficult. Next is feature detection. Feature detection identifies important points such as corners and edges. These features should remain stable under scale and rotation changes. Algorithms like SIFT, SURF, and ORB are commonly used for this purpose. Feature matching combines descriptors of feature across images. Distance metrics are used to measure similarity. Incorrect matches are removed using ransack to ensure accuracy. So next is epipolar geometry. Epipolar geometry defines the relationship between two camera views. A point in one image corresponds to a line in another image called the epipolar line. The fundamental metrics represent this relationship mathematically. This reduces the search space for matching points. Next is triangulation. Triangulation uses multiple views to estimate a 3D point. Each camera forms a ray toward the object, and the intersection of these rays gives the 3D position. The accuracy depends on proper camera calibration and correct matching. Next is SFM, structure from motion. In structure from motion, we estimate both camera motion and scene structure. The result is a sparse point cloud representing the scene. Next is bundle adjustment. It is an optimization process. It minimizes the reprojection error, which is the difference between observed and predicted points. This improves accuracy of both the camera parameters and 3D points. Next is MVS. Multi-view stereo is used to generate dense reconstruction. It estimates depth for each pixel and produce detailed 3D model. So here is the complete pipeline. We start with image acquisition followed by feature detection and matching. Then we estimate camera parameters, perform triangulation and apply bundle adjustment and finally generate a dense reconstruction. This is the complete pipeline of this. So as well as scene reconstruction faces changes such as occlusion, illumination changes and lack of textures. Noise and high computational requirements also make the process difficult. So modern approaches use deep learning and neural rendering technique. NERF is a popular method that produces high quality and realistic 3D reconstructions. Next is application. These techniques are used in autonomous driving, robotics, augmented reality, and 3D mapping application. Scene construction from multiple views enable accurate 3D reconstruction. It combines geometric principles with computational methods. Future development focus on AI based real-time system. So, thank you.